You might come across a molded case circuit breaker on a project and not know exactly how it should be adjusted to provide the best possible protection for the equipment. Or you might see a molded case circuit breaker and need to determine whether its settings have been adjusted correctly or not. The breaker you see here is a Schneider breaker. It has 3 adjustment dials: IO, IR, and ISD. Very few people can accurately identify what each of these adjustment dials is for, and exactly how they should be set based on the connected equipment. So stay with me until the end. These breakers are extremely precise, as long as they are adjusted with the same level of precision. Imagine you have an electric motor rated at 185 kilowatts. The power factor is 0.8, and the current listed on the motor nameplate is 334 A. If you don't have the motor current available, you can calculate it accurately using this formula. Now that we have obtained 334 amps, we can properly set our circuit breaker to protect this electric motor. So, whenever the motor current exceeds 334 A, the breaker will trip and disconnect the circuit. Alright. Now let's move forward step by step and start by adjusting the left adjustment dial, labeled IO. The IO setting range is from 160 to 400 amps. Since our electric motor draws 334 amps, we have 2 options for this setting. If we set IO to 320, the breaker will trip as soon as the motor starts. So we set the adjustment dial to 360. This means that IO is related to the load current of the consumer. One important point to note is this: if the motor were drawing, for example, 360 amps, we would no longer be allowed to set IO at 360. In that case, we would have to choose the next higher range, which is 400. Otherwise, we would constantly deal with unnecessary and unwanted trips. Now let's move on to setting the IR adjustment dial. Pay attention. We set the IO adjustment dial to 360. So if IR is set to 1, 360 multiplied by 1 equals 360. That means our circuit, or in other words the electric motor, if it reaches 360 amps, the breaker will trip. Now, if we set the IR adjustment dial to 0.98, that means 360 multiplied by 0.98, which equals 353 amps. So if our motor, or any connected load, draws 353 amps, the breaker will trip. And likewise, if we set the IR adjustment dial to 0.95, that means 360 multiplied by 0.95, which equals 342. In this case, if the load draws 342 amps, the breaker will trip. The IR adjustment dial is used when we want a more precise current setting. Our electric motor draws 334 amps. We set IO to 360. This means that if the motor drew more than 334 amps, the breaker would not immediately detect it, and the motor could be damaged. But with proper IR adjustment, we bring the breaker's trip current closer to the actual load current, which here is the electric motor, so we can prevent damage to the motor. So far, I hope you've understood how the I/O and IR settings work, and what the whole idea is about. Now we move on to setting ISD, which we'll examine together. In many cases, all the designs and installations are correct, but the breaker settings are not adjusted properly. Because of this, the entire electrical installation suffers from problems and unwanted power outages. Now let's go into the ISD setting, so I can explain it to you. Of course, it involves calculations as well. The term ISD means short circuit time delay. That is, during a short circuit, we give the breaker a certain amount of time to disconnect the power, either quickly or with a delay. After that, we move on to breaker B. In breaker B, we want the breaker to trip at currents above 414 amperes. So, we set I/O to 450 amperes. And we adjust IR to 92%. Which gives us a trip current of 414 amperes. Alright. Then we move on to breaker A. In breaker A, we want the breaker to trip at currents above 800 amperes. So, we set I/O to 800. And we adjust IR to 1. Which results in a trip current of 800 amperes. Now we need to set things up so that protective coordination is done correctly. That means if a short circuit occurs downstream of breaker D, only breaker D should trip, and breaker B should not operate. If a short circuit occurs downstream of breaker C, only breaker C should trip, and breaker A should not trip. If a short circuit occurs downstream of breaker B, only breaker B should trip, and breaker A should not operate. And the same logic, step by step, must also be applied to breaker A. The goal is simple. For every fault, only the breaker closest to the fault location should trip, not the entire system. Alright, now let's move on to the ISD calculations. As I mentioned earlier, we must start the ISD calculations from the lowest breaker, which in this case is breaker D. For breaker D, we had set the trip current at 288 amperes. To set the ISD range, we need to multiply 288 by 4. Where does this number 4 come from? Don't rush, there's a calculation behind it. And I'll explain it in detail shortly. Now, 288 multiplied by 4 equals 1152. The value 1152 amperes is the short circuit setting for breaker D. This means that if a short circuit occurs downstream of breaker D, as soon as the short circuit current reaches 1152 amperes, breaker D will trip. Pay close attention here. 288 amperes is related to the overload setting of the breaker. But 1152 amperes is related to the short circuit protection. A short circuit occurs in a fraction of a second and produces a current of several kiloamperes. The role of ISD is to interrupt the breaker at 1152 amperes. Prevent the short circuit current from rising further. Avoid tripping upstream breakers. And protect the breaker itself from overheating or damage. Now let's move on to breaker B, which is the second breaker from the bottom, and perform the ISD calculations. For breaker B, we had set the trip current at 414 amperes. To set the ISD range, we must consider the short circuit withstand level of breaker B to be 1.5 times higher than that of breaker D. That means we multiply 1152 by 1.5, which gives us 1758 amperes. So if a short circuit occurs downstream of breaker B, the breaker should trip when the current reaches 1758 amperes. Also, if for any reason breaker D fails to clear the short circuit, for example due to a fault or improper adjustment, and the short circuit current rises and reaches 1758 amperes, then breaker B will trip and disconnect the circuit. Alright, now a question comes up. What ISD range should we select so that the short circuit is cleared at 1758 amperes? To determine the ISD range, we need to divide 1758 by 414, which is the overload current setting. Doing this calculation, we get 4.17. But there is no ISD range of 4.17. So we must select the next higher available range, which is 5. Since we chose a new ISD range of 5, the short circuit trip value changes, and we must calculate it again. Now we multiply 414 by 5, which gives us a new value of 2070 amperes. This means that if a short circuit occurs downstream of this breaker, the breaker will trip when the current reaches 2070 amperes. Now what should we do so that if a short circuit occurs downstream of breaker B trips first? And if for any reason, such as a breaker fault or improper adjustment, breaker B does not clear the fault, then breaker A trips next. So, just like the previous breaker, we need to perform the ISD calculation for breaker A. We take 2070 and multiply it by 1.5, which gives us 3105. Now we divide 3105 by 800, which results in 3.8. There is no ISD range of 3.8. So we select the next higher available range, which is 4. Now we multiply 4 by 800, and we get 3200. This means that if a short circuit occurs downstream of breaker A, or anywhere below breaker A in the system, and the short circuit current reaches 3200 amperes, breaker A will trip immediately. For the last breaker, breaker C, if we set the ISD range to 4, then by multiplying 4 by 186, we obtain a value of 744. We can even set the ISD range to 6, which gives us 1116 when multiplied by 186. This is also acceptable, because it is 1/3 of the short circuit setting of breaker A, and therefore no coordination problem occurs. Thank you for staying with me all the way to the end.